Hey everybody, and the review will be posted tomorrow. So let's keep getting calling this stuff here. Let's raise the platform up some more. Let me look at their chat here in a second. How's my onliners doing? Itch my nose. Itch. It's a great way to start a video, right? Probably if I didn't say anything, no one would ever notice. We are 30 seconds or so away from class time. Fantastic, fantastic. Hey, everybody. Good to see everybody. We are moments away from class. Looks like you brought me some food, right? Oh, they're actually really good. You don't have to give me any. I'm fine. Are those like the octopus, or what are they? Ooh, tempting everybody. Did you bring enough for the whole class? If everyone shares. You see, there's like those things where the teachers would say that to a kid, like kids eating like M&Ms, like, did you bring it up for the whole class? They're like, yeah! And then they just like hand M&Ms to everyone. I want to be that kid. I'll go back in time and do that in every single class. It's such a snarky thing for a teacher to say, did you bring enough for the whole class? Of course, I don't mean it. I'm just having fun. Like, yeah, Brian, you said it. Okay, so let's open Zoom. I swear it moves that. Okay, we've now got everything going. No double play right here. I want to not join with audio. Now let me start screen sharing this. Start screen sharing. That's all. Cool. There we go. Let me pin my video. Pin video. Pin. Pin. Pin video. What else is that? I don't want to view this. Request. There we go. I want to watch this one. Cool. I think we got it working now. Let me pin the video up here, get the chat going properly. The fun of working, I think the video froze. There's the pin video. All right, cool. Everything's working fine now. We're good. Dark images. That's all great. Let me get the chat where I can see it, and then we'll be booted up. We're good to go now. Hey, everybody. Class is ready. We're 1 minute in, and everything's flying smoothly. Always fun. Everyone have a good spring break? Anyone do anything crazy? I went to Hyrule. Anyone else go to Hyrule? No? Do you guys know where Hyrule's at? Not a single person? You do.
I know you're talking.
I was playing Breath of the Wild a lot of the break, and it is a beautiful, fantastic game. It's the best Zelda game I've ever played. Anyone ever play Skyrim? It's Zelda Skyrim. It's just that. It's really ridiculously awesome. You can just do anything. You can go tame a horse. You can't do that in real life, can you? Horses. So it's really cool. Yeah, it's basically Skyrim. So Will's impressed by this. It's Zelda Skyrim. Pretty awesome. Ridiculous. You can throw bombs at fish. That's cool. That's how I go fishing. I see a school of fish. I just throw a bomb at them, and I just go in and collect all the fish. It's a lot of fun. It really is great. But yeah, so go buy a Nintendo Switch if you don't have one. Or a Wii U, which those are going to be cheaper. Frankly, probably do that because Nintendo Switch doesn't have anything yet. Anyways, that's what I did. Anyone else do anything cool? I went home and saw my parents too. Did that. They were nice. We talked about their will. Fun times. So anything else? Surely someone has a story. Little one. Yeah, it did. It snowed in Kingsport too. Like, Kingsport got the schools closed for a dusting. So maybe my other Kingsporters will admit to that too, that Kingsport had their schools closed. Anyone else? Do you raise your hand? Went to Texas, roommate got a tattoo and drunk. You get 5 points for best story. Snow, you get 2 stories for the 2 points for the snow. I worked for 7 days at Texas Roadhouse. It was almost as fun as the beach. I think there's a little sarcasm right there, maybe. So Texas Roadhouse, good stuff. Well, get some money. That's good. I played bingo in Kentucky with my grandmother. Old people are the best. Oh, I love, some of my favorite memories was my grandparents would invite over their neighbors, and they would always teach us games like Pass the Trash or Follow the Queen. We'd play card games, and we would do that late at night. You know, I don't remember if they would buy us a whole bunch of junk food, but that would make it even better. If we went to the store, bought a whole bunch of junk food, and then they're like, we're going to play cards, and you're going to drink soda and eat junk food. Be awesome. Stuck in the blizzard in Boston. Oh, man, that was craziness. I'm glad you got back, or maybe you're not back. I don't know. Well, Fun times. I'm glad you're here. Glad you're doing well. And let's get started. We're going to start up. We're 4 minutes in. 4 minutes in. Get some class learning going. Kind of, you just get your jollies out. You just work it out at the start of class. You gotta enjoy yourself a bit. Life's not all about stats, right? Class over, done. Let's go home. No. You guys want to learn today? Sounds like a good plan. I think we'll even get to some of the assignment today. When am I going to learn? I can't click on that. For the life of me, I do not understand why that doesn't work. I don't know if it's my class or all classes, but that has stopped working for a long time. So here we are. We have gone through a lot of this. We have learned so much. And we've talked about last time ghosts or aliens, which were much better than ghosts as I swing through this. If you did not see last lecture, please go back and watch it with the ghosts and the aliens. Last lecture is posted, correct? I think I would have gotten an email now. Sometimes the post is weird. Please email me if the lecture isn't posted within 24 hours. The posting of it is weird. Just the Canvas posting, good, it's up. And they get posted to the YouTube also, and I think I'm just going to let them be out there on YouTube. But it's just so weird. Do you guys remember the assumptions that we must have? Condition 1? No! They said in class QQ, you lose all your extra credit. It's all gone. QQ straight enough, no outliers is gone from our heads. No more do we remember QQ straight enough outlier. Christina gets the extra credit, 5-point extra credit of the day for Christina for saying some randomization. Number 1, random. Number 2, raise your hand in class or online. Number 2, 10%, Sequoia with a 5-point 10%. I'll even throw Catherine one too, and another one for Christina. Random, 10%, and see online, they can type it, they can get ready, they can be like, he's gonna ask the next one. The next condition is where you have to pause, success, failure. Another 5 to all you guys racking it up today. Online is destroying you guys in class, come on. Does everyone understand these conditions? Let's take a look at them. They'll be here on the slides in a second. We have random, 10%, and success failure. And we can do some example problems here coming up in a moment. But what does random mean? It means whatever you're sampling must be sampled randomly. So I like that condition. I think that's a great and easy condition to remember. Randomization condition just means things are sampled randomly. Nice and easy. 10% is where people get confused. Because what do you think is better, sampling more or less? More, but read the condition. We want our sample to be less than 10%. The reasons for this breaks down into the whole finite samples and AP statistics. We don't want to get into it. You can write me a paper on it. I'll read it and maybe I'll learn something more. I think I showed you guys the article last time, did I? It shows how the mathematics break down. Yes, no? All right. Just if you want, for your own reference. I do remember it now because it says a puzzling condition, and watch, there it is right there. This is not the right one. It's this one right here. It's like a puzzling condition. There it is. A common assumption about why do we need the 10% condition? And then it shows how the mathematics work out, and it shows how the error is calculated. So you can see after about 10%, the error in your calculation due to finite populations gets problematic. Now, really quickly, why do I say finite populations? Because could you oversample an infinite population? You'd have to sample 10% of infinity. Is that possible? So these rules only apply to finite populations. I've gone way too much into this. What do you need to know about the 10% condition? The way to check it is that you've done what? How do you say you've passed the 10% condition? You would say my sample of sample size blank is what? What does it say? My sample of sample size blank is less than 10% of the population. So what if I go out and sample 300 UT students? Did I pass? Nice job online. Extra credit there and extra credit online too. Did I pass the condition if I sample 300 UT students? Yes or no? Yes, because 300 is less than 10% of all. And you could even say, given that there's more than 3,000 students at UT, 300 students is less than 10% of all the students at UT. And that's a reasonable assumption. You might not know exactly how many there are, but I think we have around 30,000. What if I sample 25,000 students at UT? No, then we have violated the 10% condition. This violates the 10% condition because 25,000 is more than 10% of the UT population. Do you see how on a test you could answer that question? These are easy points on the test. This is pure memorization, and it's something I've been getting into when people ask me how to prepare for the test. The Quizlet is one of the things on this test that I've worked harder on this Quizlet. Please email me if you want it. It's also in an announcement or two, I think. But these are pure memorization. Random, 10%, success, failure. Problem is, when we get to the third condition here, we have the success, failure condition. Why are we using the success, failure condition? Because the data is what? The data type, or the variable type, is something either happening or not, a yes, no response, categorical. Christina, you're on fire today, love it. So it's categorical, does that make sense? Because we can have successes. In some of your homework problems, you're seeing if an apple is good or bad, if you've done the homework, the truck with apples problem. And so if the apple is good or bad is a yes, no question. You're seeing if someone will default on a loan. Defaulting is a yes, no question. You're seeing if children are nearsighted. That is a yes, no question. Do you see how these are all categorical responses? Was the child nearsighted? We'll switch here in a moment, but it's important to recognize in chapter 15, part 1, you are dealing with categorical questions. And this is where people get destroyed on the test. It's because when we get to 15, part 2, we will deal with what kind of questions? Quantitative questions. Extra right there, spoke up, I love it. Quantitative questions. And that's where people don't know what to do on the test. They're like, I don't know what formulas to use, Brian. And they start plugging things in spots they don't belong. But you have to identify what the question is asking and what type of variable we are talking about. That is what is required to do what is considered probably some of the hardest questions of test 2. And they're not that bad if you can walk through the problem and identify the parts. And we'll be doing a few of those today at the end. Lots of great stuff. Last lecture was great. These are discrete random. That is correct because we can have that there was 7 children who were nearsighted, 8 children who were nearsighted. You can't have 8.5 children who are nearsighted, but it's a discrete random event. How many children were nearsighted? So there were 8 nearsighted, 9 nearsighted, and those are categorical occurrences. But it is discrete random because you can only have whole numbers of how many children are nearsighted. Very, very true. Very nice job. Nice pullback from earlier on. There's the conditions. And why do we even care about conditions? Oh, man, Brian, I hate this condition junk. Why are we doing the conditions? And this slide alludes to it. The reason we are doing conditions is because when we meet the conditions, we can draw, say it for me in class, students, we can draw the what? What's this called? Oh, if they're saying it online, they can't even see it. They said the normal model, the normal curve, exactly. We can draw the normal curve. The normal curve allows us to do the 68, 95, 99.7. And that's our point, is if we can do the normal, we can do the 68, 95, 99.7. And look at what we constantly are solving for. When we solve this, we are solving for a mean and standard deviation. In classes, you got to help me out. The mean of this distribution is P. The standard deviation is, it's on the screen, P times Q over N square root. P times Q over N square root. And this is for this chapter specifically. You will get the formulas for this, but it doesn't hurt to memorize it and know it. That this right here is normally distributed, and I think it's on a slide previously. This model will be normally distributed, there it is, with a mean of P and a standard deviation of P times Q over N square root. Go ahead, question. Bingo, we're in 15, we're doing a slight review of 15.1, dealing with categorical data when we look at like how many people will default on their loan, which is a great question on the homework assignment. So if I told you 7% of people will default on their loan, then what did I just tell you right here? If you go out and take a sample, which is what that P hat stands for, if we meet all the conditions, like we sampled 200 people and we expect 7% to default on their loans. There's one last thing I want to say. Random 10%. Oh yeah, we randomly sampled them. I was like, what's the last condition? We randomly sampled 200 people, and we know from large empirical data that 7% will default on their loan. Do we meet all 3 conditions? And I'm doing a homework problem right now for you. Do we meet all 3 conditions if I say we sample 200 people randomly, and we know that 7% will default on their loan? Condition 1, explain to me in word format on the test. Random, nice job, onliners. Is it met? And why? Brian stated that they were randomly sampled. That's a great explanation right there. Condition 2.
You should say
Careful, careful, careful. This is confusion I've heard. Don't worry. You're.
maybe because we don't know the population.
This is going to be all people in the United States. Great question. This is going to be we're a national bank that is across the United States, and we're taking a sample of 200 people.
Yeah.
Do we meet it or not? Careful. What's the condition? 10%. And what do we? Yes, because how many people are there in the U.S.? Like, I think 300 million-ish, 320 million now maybe. So is 200 less than 10% of 320 million? Yes. You see, we're fine. It's an oversampling thing. So people get killed on this condition on the test. It's usually 2 points or so because it's true falses, but it's less than 10%. We'll probably never ever do that to you. That'd be a dirty trick. And truthfully, let it pass. But that'd be a mean trick. I think the condition says less than 10%, but it's not like things explode at 10%. But that's a good question. And then the next condition is success failure. Who wants to tell me, and this is what you must do on the test. So exactly, nice job. Wilkin wrote a great thing right here. Patrick wrote, there are more than 20,000 Americans, or more than 2,000, which I really read the whole thing. There's more than 2,000 Americans, so that 200 is, we have not oversampled. Great way of answering it. I like it. Nice job. 5 extra credit. Last condition is success failure for this. Success failure states there must be at least 10 successes and at least 10 failures. Nice job. And NP and NQ are at least 10. Online, you're killing it today. So what is NP? N is sample size. P is probability. What was my sample size? Write it down and work it along with me. Sample size was what? N is what? 200. P is what? So what's 7% of 200? 14. Guess what NQ will be? If NP is 14, NP and NQ add up to 200. So NQ is 186. Does that make sense? So, well, we could take, what is Q? Q is equal to, and that's my best Q. Q is equal to the complement of P. Q is equal to 93%. 93% of 200 is 183. If you times 200 times 0.93 is 186. Does that make sense? Questions? Sure. NQ plus NP equals N. This is what I do in my head to double check it, because you have the amount of successes you expect and the amount of failures you expect. So if you find NP, you can find NQ by adding them up. You could also multiply 200 times 0.93 and 200 times 0.07, and you will get 186 and 14. So nice job. The last one right here is 0.93 times 200. Sequoia, 0.93 times 200. Does that make sense? Because Q is the complement of P. It's good questions. Q is the complement of P. Gotcha, cool. Just making sure everyone's got it. Ask all the questions you have. This is like a little example problem of it. So what does this give us here? What did we do by solving all of these? By saying we meet all the conditions, we can now say it's normally distributed. When we go out and take a sample, we would expect that sample to be normally distributed, and what do we expect to see? We'd expect 7% of people to default. And let's go over here to David M. Lane Applet now. This ELQ is a more difficult ELQ, and I will be putting a 8% bonus on it. There are some questions on this ELQ that are very challenging. So I will be giving an 8% bonus added on to whatever you get. There are questions that go above and beyond, and if you email me, I'll probably be like, there's a few I'll help you on, but there's 1 or 2 that are really confusing. I can do them, but they usually, the best way to do them is on the TI calculator, and it's kind of hard to say to somebody, press this button. And I feel like the learning potential in them is a little bit low. Basically, I realized like, oh no, I put those in there. And that's why I'm giving you 8%. So if you decide to tackle them, and I'd say there's only 2 or 3 of them, so there's really only 4 or 5 points. So you're getting a bonus above and beyond, so you can make over 100 on this ELQ. So if you make a 95 on this ELQ before I change grades, how should you feel? If you make a 95 on this ELQ, how should you feel? Good, because what do you really have? A 103. So you've made above 100. So just realize you've got some fluff room in this. They're the ones that deal with, it gives you a number table. but it's really easy on the TI calculator. And I was going to write an email to someone today, but I was like, I'm really just telling them how to punch buttons in the calculator. I'm not teaching them anything. So I didn't want to write the email because I'm not helping them, and you know what I mean? We're here to learn. And then I kind of realized this question was kind of a meh question. So I was like, I need to remove it. But I can't remove it now that the quiz has been active and people have done it. Mike Pearson, thank you. Okay, so what do I need to find? The standard deviation. What's the formula? I forgot already. P times Q over N square root. Everyone got that? P times Q over N square root. And look at how the numbers change. Our bank will go out of business if 13% of people don't pay their loans back. Do I have something to fear? My bank will go under. We will cease to exist. They'll close our branch. Do I have something to fear if more than 13% of people don't pay their loans back? Nice job, Michelle. If more than 13% of people don't pay their loans back, bank, we're done. We're foreclosed. I don't think they can do that to banks, but do I have something to fear? How many standard deviations is it at least away? You can see it visually. It's at least 3, extra right there. It's at least 3. Look at this. We have our standard deviation. What is the mean right here? The mean of this distribution is what? 13, right? I mean 7. What did I say we don't want to observe? What percent do we not want to observe? Or we'll cease to exist? 13. So observation, does that make sense? Minus mean, does that make sense? That's the distances away. You can see that. Over what? My standard deviation. And what's this going to give us? A what? What is that? It's a z-score. Do you see how 13 would be about 3.3 standard deviations above the mean? Is that an odd occurrence? We could then figure out the probability of that right here, and the probability of it is basically 4 in 10,000. You can't even see it, it's so small. It is very unlikely that we would have this, only about a 4 in 10,000 chance. It could occur, but it is highly unlikely. I'm a terrible bank, love it. So once again, the formula I used there to get the z-score was p hat, because these are all the p hats that could occur. Could it be that 8% of my loans don't get returned? How about this? How about this? Anything in here is what could happen when we give out 200 loans. Does that make sense? And then we would say, what is the z-score, as in how odd is that? And then we could figure out the probability by using the David M. Lane applet. Now on a test, we could ask you, is it very likely my bank would foreclose? Given the z-score of 3.32 and you can't get the area, does this seem unlikely? It does. Explain in words on the test. Why is this unlikely? Because an observation with a z-score of 3 would only occur less than, something above that would only occur less than 0.0015% of the time, or excuse me, 0.0015. If you turn it to a percentage, it's 0.15% of the time. But the probability of that is less than 0.0015. And where do I get that from? I get that from above 3. Because you have 68, 95, 99.7. Above here is 0.15%. So the probability has to be less than that. Does that make sense? That means it's highly improbable. So I would feel pretty safe. I'd be like, it's very unlikely. I'd probably take the risk on this. And this is where people do like risk assessment and stuff. Like, should I take this risk? Should I do this? These are the harder questions on the test. If you look at all the steps I had to do this, I had to identify what is my P. This is the true proportion of people who will not pay back loans. I had to identify P hat, what I might observe in a sample. I then turned it into a z-score by finding the standard deviation and dividing the distance over the standard deviation to get a z-score. This is what your homework will be going over, and I'll probably do some more at the end, and we'll get back to this. But we're about to switch gears and see the magic of the central limit theorem. Go ahead.
They're not in equal in hat.
Do what if it's
Like our actual outcome.
not NP hat yet? Only NP-NQ, and they need to be greater than or equal to. And some things might say greater than, some things might say greater than or equal to. That's another because it's like a magic number. And if we get into number theory, numbers don't even really exist because they're infinitesimally small. Because what's 10 minus 10? So 10 encompasses nothing. Well, think about it. How many numbers are above 10? If you look at, there's an infinite space above 10. And sorry, this is like all number theory stuff. Do you guys know what I'm saying? If you talk about 9, like 0.99999 and 0.10, 10 is infinitesimally small. So it's almost a non-point to say, like, what if it is 10? It's like, who cares? Do you get it? It's number theory. I don't know. It's stuff that hurts your head. Anyone ever take a theory course in mathematics? Good. Don't do it. You don't want to. So is p hat is always dependent on the sample? Yes. P hat is always dependent on the sample. P hat is for a sample. P hat is a sample. And that's what we're drawing here is we're drawing the sampling distribution of what could happen. What I just drew for you here is all the possible p hats. Inside of this distribution right here is little p hats of things that could occur. Does that make sense? When I go out, and I'm drawing p hats for those online who can't see, but I'm going out and I'm sampling, and these are all these p hats that could occur. Does that make sense? These are things that could occur. And something up here, there's not really any p hats up there. Yes, there are, but they're extremely unlikely by random chance. And what are we doing to get our sample? Randomness. So if it's true that the population is 7%, we should see something close to 7%. So this is when we go out and sample, and that's what blows people's minds about this chapter, is you know the truth, and you're saying if the truth is 7%, then we should see something close to 7%. So in chapter 15, you know the truth. You know the truth. And we went through these examples last time. Feel free to watch the video, and you will see me go through the aliens examples, aliens, and aliens, or extraterrestrials, if you watch the show. That's the key. So, anyone watch the show? They don't say aliens earlier, they just say extraterrestrials. It's awesome. It's like extraterrestrial beings. It's so much fun. I miss it. Still got a few more seasons to watch. It's like sometimes they make an argument where you're like, yeah, maybe, and then other times you're like, oh my gosh. It's like, was Jesus really an alien? And you're like, probably not. But I'll hear you out. I want to be entertained. So it's a fun show. And then you got Giorgio. Where you at? Where you at, Giorgio? You guys know who Giorgio is. Anyone who's seen the memes knows Giorgio. Hilarious. And you know when someone gets self-aware of their meme nature and they become like obnoxious? He never does that. He kind of has this persona that's been all the way through. So check out some Ancient Aliens. It's worth your time. Okay. What about quantitative data? That's our little transition, our little 2-second break. So what about quantitative data? We're going to switch gears here, and we're going to go to quantitative now instead of categorical. Make sense? So all of a sudden, everything changes. Now we're going to roll dice. So there's our dice rolls. I knew they were coming up. So with rolling the dice, what kind of distribution do you get when you roll a dice? You get a quantitative histogram distribution. Exactly. And so how does it look? How does the dice rolls look? If we kept doing this, I know that has a shape to it. Does that look unimodal, bimodal? What is it? Symmetric. And what else? Uniform, extra credit there, and extra credit there. I'll throw an extra credit to the online or two, and another online extra credit there. Caroline, I don't think you've given you a today. Nice job. 5 points to Caroline. Or Carolyn. So it looks uniform, and it looks symmetric. Which uniform would be symmetric, still a good word to apply, because it's just uniform, just like I call it a bread box. But what? I don't know what's going on here. I'm confused. Because all of a sudden now we're going to take 2 dice. We're going to roll 2 dice in our hands and drop them, and we're going to see what we get. What is the only way to get 1 when you roll 2 dice and average them together? 2 ones. I know you mind me mind meld, both of us. Mind meld, this is just the line of mind meld right here. So you roll 2 dice, you get a 1. What's the only way if you roll 3 dice to get, when you average them together to get a 1? When you roll 3 dice, here's what we're gonna do. Everyone, you 3 dice in your hands, you drop them. What did you roll? Did you drop your dice? What'd you roll? Tell me your 3 dice. Look at them. Look at your 3 dice. What'd you roll? Anyone online? 4, 6, and 2. We add that together, that's 12. 4, 6, and 2 is 12. We divide by 3, we get 4. So your average was 4. Who else? Someone wrote 3 ones. Whoa, Montana got 3 ones. Extra credit right there, Montana, for rolling 3 ones. What was the average of Montana's dice? It was 1. Well, we keep doing this and increasing the number. If you roll 20 dice, what is the only way to get an average of 1? Here, take your handful of 20 dice. It's a lot, don't spill any. And just drop them. Okay? What'd you roll? Don't worry, we don't got time for that. So with the 20 dice, what's the only way to get I'm saying it. What's the only way to get an average of 1? Does that seem probable? What do you think is more probable? And just look at the graphic. Well, yeah, you'll get some 1s, some 6s, some 3s, some 4s, some 5s. Nice job online. You'll get all different numbers. And what are they probably going to average up to? Around 3 or 4. Seems likely, right? When you look at 1, 2, 3, 4, 5, 6, you get 1, 2, 3, 4, 5, 6. What's between those numbers? What's between 1, 2, 3, 4, 5, 6? What's between 1, 2, 3, 4, 5, 6? Look, 1, 2, 3, 4, 5, 6. What's between them? What number's between my hands? 3.5. Look at where the center of this is. Does that make sense? 3.5 is not an observation that occurs. Nice job, onliners. 3.5 is not something that can occur on a dice. But if you roll multiple dice, you could get an average of 3.5. Does that make sense? So that's kind of the true, because 3s and 4s are the most likely in the long run for the average. But when we average it out, you get 3.5. And you look at all of these, they're all peak at around 3.5, except for this first one. And this is going to get to the theory that blows people's minds. Too much ancient aliens. So the sampling distribution for the large samples of n is skinnier when compared to small sample sizes. The large n, the closer the sample average is to the population mean, law of large numbers. In the long run, think about this, in the long run, the dice will average out to the true average. Does that make sense? Or it's more likely. You'd say, well, yeah, just keep, someone says, oh, this dice seems a little bit off. I rolled it 3 times and I got 3 1s. Roll it 50 more times. I mean, if you got 50 1s, we'd be like, okay, that seems extremely improbable then, right? Because could you roll a dice 3 times and get 3 1s? I'm not saying it's very likely, but yeah, we could figure out the probability of that. It'd be 1/6 to the 3rd power. Probability you get a 1 and get a 1 and get a 1. I think it's 1 over 216, so it's about less than 0.005%, about 0.0046 or so. So very unlikely to have happened by random chance, but still possible. Well, what's the possibility of it occurring with 100 dice or 20 dice? Well, that'd be 1/6 to the 20th power. And I'm sorry, I'm not that quick on mathematics. I'm quickish, but I can't figure that one out off the top of my head like that. But that's ridiculously small. That's not happening. You can't even see it on there. So with this in mind right here, we would say that is extremely unlikely by random chance. Wouldn't you say if somebody rolled 6, 20, or 1, or 6, 1 20 times on a dice, and they didn't just plop it. They took a real, and they threw it across the room, and it rolled 1, 1, 1, 1, 1, 20 times. Would you say that's a random dice? Do you think that's, or do you think, no, that's so unlikely, I don't think that dice is fair? I would say so too. And someone, you see the people who don't do math, they're like, that seems possible. Like, no. That's 1/6 to the 20th power. And if you count the first one as a free dice roll, like, hey, whatever we rolled first is just kind of random, and then we're going to see if it continues that sequence, 1/6 to the 19th power. If the first one is just considered, because it'd be odd if it rolled 5 every time, right? So given that, the first one's just kind of okay, whatever it rolls the first time, sure. And then if it continues that's really odd. Lots of ways to talk about that. So what do we notice here? The shape of the sampling distribution resembles the normal curve. And this is what we're going to break down right here. How did this happen? Why are we getting the normal curve? What in the world is going on? And it is the central limit theorem. Keyword at the end of this is theorem. This is not the central limit guess. It's not even the central limit law of mathematics. In mathematics, we have theorems, and that means it works. A theorem is not even proven. I guess it is proven. It is. It's mathematically proven, I should say. Science doesn't prove anything. Science proves nothing. Science only shows evidence. You know that, right? All science does is show evidence, or fails to show evidence with the null and alternative hypotheses and all that. But math proves things. And the central limit theorem is proof. Nothing wrong with science. I love science, but it can't prove things. It's just how science works. It's in constant search of the truth. But the central limit theorem is a fundamental theory in statistics, reading from the slides. Let's not do that anymore. What it's going to do is it's going to look at the possible averages of the samples taken over a population. So what we are going to look at is the two conditions. What we need here is one, for n to be large enough. And I really only care about two of these conditions. Let's go to the conditions. Because what do we have going on here? Condition one,
Random.
boom, you get 5 extra credits. On it. Beat the online. They're typing it. Condition two, there's an extra credit on fire day today. 10% online is getting charged again. Each one of you gets a 2 times extra credit online. And then condition three, pause. Nope. Almost said it, right? But why do we pause? On condition three, we have to do something, and I want to make sure this is clear. Condition one and condition two are like this for the rest of the class, and this is no joke. Never tell me that QQ nonsense again. So condition one and condition two for the rest of the class. Ooh, online's got it. Condition one and condition two is random, 10%. That's why we made sure we knew those. That's why we reviewed to start. But condition three is where you pause. You think, you just meditate for a while. And you say, are the data, I don't know. Is the data I'm working with categorical or quantitative? We're working with dice rolls here. When I roll a dice and look at the outcome, is that a quantitative or categorical outcome? Quantitative, because it's a number. Since it is quantitative, we need to look at the large enough sample condition. We just call it the large enough a lot of times. So condition one, random. Condition two, 10%. Condition three, large enough. You're fine to just call it that large enough and large enough. Large enough.
Because every time I hear
what we mean by the large enough condition is this.
Going.
It's beautiful. I love this.
Was it dark? It was fun.
Central limit theorem. Yay. When this page stops existing, I'll be so sad. What we looked at to start was a uniform distribution. And we said if we rolled the dice twice and we averaged them together. Remember what we're doing? We're going to roll 2 dice and then get the what of those 2 dice? Yeah. And look, do you see how this is doing? Ooh, that was an odd one, wasn't it? The one down there. Because look at what's happening. It's not purposely taking a high and low one, because you can get, that's the oddest I've ever seen, actually. And it was on cue almost. Because it's not going to pick high, low, high. It's not going to do that. Each one of these selections is what? Condition one, random. So, when you think about it, kind of it's like we'll get a low and a high, but it doesn't mean we will. Because you can get a high and a high. You can get a medium and a low. These are random, so it's just going to be random where they are. And if we were to keep doing this, we would build a distribution, and I just did it hundreds of thousands of millions of times now. What you saw me doing here has been reiterated 2.7 million times now. And I have a new distribution, and this distribution is the distribution of the mean of rolling a dice twice. Does that make sense? How did I obtain one observation in this distribution? I had to do what? How did I obtain one observation? What's one observation down here? Take 2 dice and average them. These are key concepts. This is where people get confused on this. Because they're like, oh, this is just chapter 5 all over again. It is and it isn't. Because this is for the distribution of a mean. And if I were to increase this sample size, because is that the normal? And it's unimodal and symmetric. But is that the normal? You ever seen a normal look like that? No, it doesn't look like normal to me. What if I increase it to 5? How do I get one observation in the distribution of the sample mean of 5? I do what? I take 5 dice, drop them, and then what do I do to them? Take the average. Do you see how that's the distribution of the mean? Does that make sense why this is the distribution of the mean, of a sample mean? Does that make sense? Last time was the distribution of a sample proportion, because the proportion of people who don't pay their loans, the proportion of children who are nearsighted, the proportion of bad apples on the truck, which is a yes-no question. Did they pay their loan? Was the apple bad? Was the child nearsighted? Now this is the distribution of the sample mean. What was the average of the 5 dice rolls? And as the sample size increases, the distribution of the sample mean will become more normal. What if I increase it again? It'll just become more normal. This is the distribution of the sample mean of sample size 10. How do I get one observation down there? That's it. And do you think if I roll 10 dice and I find the average of 10 dice, that it'll be something way, how would I get something way up here? If basically what? All the dice have to be up here to average that. Does that make sense? So when you roll 10 dice, everything's usually going to wash out a lot better. You might get something odd like that on cue. Really not, I'm not making this do it. But usually you'll get something normal like that. Another odd one. I was going to think I was psychic. But it's aliens. Aliens. So this is even more normal. But watch this. What else do you notice is happening to it as I increase the sample size? Tighter. Those are the two things of the central limit theorem. It states, I'll try to explain again, Christina, we'll go into more depth right here. So what we're doing here is I'm rolling 25 dice. I'm rolling 25 dice. Then I'm going to take the average of all these dice rolls. To view it visually before I've done that, we're going to take 25 dice. So here's me rolling 25 different dice. And then to get one observation down here, I average those all up. And there it appears. So I'm averaging together 25 dice rolls. The only way to get something over here would be if I got 25 dice rolls that were all sixes. We're pretending this is like a number line 1 through 6 again, using our examples. So when we increase the sample size, the distribution becomes more normal and tighter. Does that make sense? I want you to see something though. Watch this. I'm going to do a random, does that make sense? Okay, gotcha, good job. This is one of the harder concepts. Okay, my standard deviation here is something I'm trying to make. Whee! Oh, dang it. Yes! What's my standard deviation? That's an elephant right there. Is an elephant a normal curve? Well, it is now. What does this new distribution look like? It looks like the same distribution, not really, but tighter. And where's the mean at? Where's the mean of my new distribution? Look at the concepts. This is key concepts. I'm already teaching you something right here. The mean of my new distribution is where? What is the mean of my new distribution? Look at the output on the side of the screen there. The mean is, yeah. Is it higher? Or is it exactly the same at 12.54 and the previous one was 12.54? Does that make sense? And what is my new standard deviation? Why did I want 5? My sample size is 25. I'm dividing my original standard deviation by what? By the what of 25? Square root. We'll see that in a moment. In the nice job online. Yes, love it. So we're going to divide by the square root of the sample size for the new standard deviation for the distribution of the means. Now I want you to think about this. Here's how this works, and this is how it makes sense. If we have one guy walking down the street, maybe this could be the population of heights of guys at UT. So we've got a bunch of people who are normal heights, right? Regular kind of everyday heights. And then we've got like UT athletes, maybe. I don't know. They're all 7 feet tall. Every UT athlete. If you didn't know that, fun fact, all UT athletes are 7 feet tall. That's our requirement. Not really. But this is what we got going on with the distribution. Got it? But if I were to average together 25 guys, let's say the average guy at UT is 5'10". Make sense? If you speak to one guy, what height would you expect him to be? 5'10". If you were to speak to 25 guys and average together their heights, what would you expect that to be? 5'10". And that's why the mean does not change. Does that make sense? If you talk to one guy at UT and the average height of a guy at UT is 5'10", what's your best guess of his height? 5'10". If you took a whole bunch of guys, like 25 guys, and averaged together their heights, you just took them at random, not purposely trying to find athletes, not athletes, take random guys, average together their heights, what's the best guess of the average? 5'10". And if you took a whole bunch of guys, wouldn't you maybe get, there we go, we found one. Wouldn't you maybe get some tall and some short and maybe some outliers? But in the end, would the whole thing kind of average out? Look, oh, wow, 3 outliers. But doesn't it eventually kind of average out? Because the mean is this, and if you keep taking samples, you're probably going to get something close to the mean the more you do it. This is where large enough comes into play. This worked here because n was large enough. So let me explain to you in detail the large enough. Nice job, online answers. Let me do a new custom right here. And let's do something ridiculously skewed. Oh, I love this central limit theorem, because how the central limit theorem works, Brian Stevens says, is if we go out and we have like this distribution right here. So we got this crazy distribution. And so we got this distribution, right? Brian said, oh, if you just take, this, well, then you take 5, okay. Okay, that's, that looks like it's near the mean. I think this mean is the blue one. That's near the mean. So this is going to look pretty normal. I'm going to keep doing it. This is Brian. Your thing's broke. Tell me I'm not meeting the condition of what? I'm not doing it. I'm taking the average of 5. Well, let's increase it. Let's go to 20. Still got to right skew a little bit. Dang it. It's looking a little good. Go to 25. That's not normal. Does that look like a perfect normal, like David M. Lane-Applet normal curve right here? Let's go down to it. Does that look like a David M. Lane-Applet normal curve? No. My sample size was not large enough. What do you notice is really going to mess it up? Because remember, it worked for this. It probably works for this right here. That looks pretty good. Not so bad, right? I mean, it's got, let me see, a little skew. What happens if we do it to the normal? Well, let's put it all the way down to 2 here on the normal. Whoa, the normal is normal if you sample from the normal. Because, it sounds potted. Whoa. What do you notice? It's like it's molding it. And the higher the sample size, the more it's able to mold it back towards a normal. Does that make sense? So the further away it is from a normal, the harder it is to get it to a normal, and the larger n has to be. So when we look at the slides right here, and we see what's going on, n of 25 works for most populations. That's pretty good. We did it for the uniform. We did it for the skew, the little skew. But then when I put in mega skew, we'd probably have to go towards 100. There's things that even don't work at 100. But here's your moniker. If it's 25, you're good unless it's really skewed. And that's really like the break point. I don't like the questions that get too specific on this because we don't go too big into it. But what does increasing the sample size do? It makes the distributions of means more normal. Now, if the distribution of single observations is normal, how large does n need to be for the distribution of means to be normal? Hint, the answer's on the screen. If the distribution of single observations up here is normal, whoops, that's not what I want. If the distribution of single observations is normal, how large does the distribution of sample means needs to be normal? Remember, it's normal to begin with. It's normal to begin with. And all increasing n does is make it more normal. It is normal to begin with. How large does n need to be? I'll throw you 10 times extra credit. I want someone to get this. No one's got it. I'll take 1. Because the original, which does that mean it'll work for 2? Yeah. Because remember, increasing n just makes the distribution of means more normal than the original. Was the original normal? So any distribution of means will be more normal. So if you take something that's normal and make it more normal, it is what? Still normal. It's like if you have an A in a class and you make an A on a test. What do you have? B. You said B. You have an A, right? I haven't been in school a while. So, but what if if you're really working hard to pull something up, like if something's really skewed, you have to make a lot of A's, right? So the higher the sample size, the more it is skewed. That's the way it works. Does that make sense? So if we have something ridiculously skewed, like I'm going to try even harder to make this more skewed. We have this ridiculous skew right here. Sometimes I can get, come on, don't do this. I think that works. There's like slick ways of doing this that work so well. Yes. Does that look normal? Nope. Probably take a larger sample size. That's because that's ridiculously skewed. See how that works. Whoa, that's how it turned out? No, it's pasting the other ones. This turned out normal. I gotta remember the tricks to doing this. That one works. This one doesn't, just because there's more spread. This one's actually a little bit more uniform when you take it in. Because think, if you slice off this, it's actually more uniform than it is skewed. Does that make sense? Like this one right previous was more skewed. This one's more uniform with kind of an odd outlier region. So that's why I hate it when we go so specific on this. What you need to know is the larger the sample size, the more the normalizing effect. Does that make sense? Why do we want it to be normal? Because we want to use the what? The what rule? The what? 68, 95, 99.7. Once we get to normal, we can start using that rule. And that's our goal. Onliners, Christine and Mackenzie, you guys get some extra right there. And look at this. As we've talked about and we said this, if one guy is 5'10" at UT, what would you expect when you go out and sample and get the mean for sample means? Like, what is the most likely thing to see when you take a sample of guys? See how this is Y bar for a sample of guys? This says, what do you expect to see when you go and get a sample of guys? It's what you would expect to see for the population for a single guy. So 5'10" is the mean for the distribution of sample means. So when you go out and sample guys, you would see 5'10". This right here states, if I go out, or excuse me, what do I expect to see when I get a sample proportion? I would expect to see the what? Kind of the true proportion of the population. Because if 7% of people default on bank loans, if I go out and take a sample, I would expect to see 7%. Does that make sense? This is the mean, or what I expect to see when I take a sample with proportions, categorical questions. This is the mean, or what I expect to see when I go out and take a sample for quantitative questions, because I'm going to get an average, right? So when I roll dice, the average for dice rolls is 3.5 for the population of dice. Well, when I roll my dice, I would expect to see in samples 3.5. The standard deviation. I love this part. I love it because we've seen this. I told you. We saw it work. And as I said, it's the central limit theorem because we can prove this works. It's not a guess. It's a theorem that works every time. So with this standard deviation right here, all you're doing is taking the original standard deviation, dividing by the square root of n. Does that make sense? That's why when I made the standard deviation 5 and I made the sample size 25, the new standard deviation was what? The original standard deviation was 5 and the sample size was 25. The new one is what? The original standard deviation is 5 and the sample size is 25. It is 1. And you can show this once again to be true. My standard deviation, let me try clearing it. Oh wait, let me do custom again. We will prove it or show with a simulation is true. Standard deviation. Can you tell what number I'm going for right now? No! I hate it when I want everything to be perfect. I am OCD a little bit. That's too low. I'll give it 2 more tries. It's not going to spend too much. Yes, yes. What did I want? No one knows what I wanted 10. So now when I run this simulation right here, guess what? It's normal, and the new standard deviation is what? You see it? 2. That's why it's the central limit theorem. This is a hypothetical distribution that exists. If you were to go out and sample from that parent population and take 25 random samples, you would get something from this. Do you see how this blue, wherever this blue one would go, and you're not going to view it unless I clear the lower 3, wherever this blue dot goes is going to come out of that distribution that we see right here. And that was actually an odd occurrence, that one that we just saw. Usually, if you watch where this occurs, we're going to get something probably closer to here. Ooh, that was an odd occurrence again. Getting some odd occurrences in here. Get some right about here. There we go, that's close enough. And then if you keep doing it, you'll see that those are right there. I mean, you can get stuff over here. They're just a little bit odd. They do occur probably about 5% of the time. So this time my psychic powers aren't working. But that's what's happening. When you go out and sample 25 from up here, you are getting something that occurs down here in average. And it's normal or normal enough. This looks normal enough for us to use 68, 95, 99.7. Does this look really skewed? No, it looks really weird, right? But not really skewed. And that will mean it comes out normal enough or as we say, the n is large enough. The sample size was large enough. So the new standard deviation in my simulation right there was 2 because the sample size was 25. 10 divided by 5 is 2. And this is the thing I was just using. I love using it. Let's do the balcony example, which I think we did last time, and maybe this time will make more sense. We did it 2 times ago now. So here we go. We have a person who wants to design a balcony that needs to hold at least 19,000 pounds. A survey of 8,000 adults from 2005 says that the average US adult, 20 and above, which are the only people we're going to allow on our balcony because it's got a chance it might break. We don't want kids suing us. Fun times. Says that the mean of the weights of US adults is 176 with a standard deviation of 61. Now, if we are going to invite 100 people on our balcony, the average person cannot weigh more than what? Ah! We don't want it to break. 190. Because our balcony is only designed for a limit of this much. How did I figure out 190? Yep. Does that make sense? So I can't have an average weight of these 100 people over 190. And do you see what I'm going to do? Is I'm going to take these 100 people together, and my balcony has a scale underneath it that divides all their weights by 100. I'm going to be like, uh-oh, I'm going to see what their weights is. Weights are. I guess their weight is, because it's a one weight average. The average of their weight is. So let's go ahead and take a look here. Let's see it. Let's go to the David M. Lane applet. Well, I'm not going to invite my friends. The friends I'm going to invite on this balcony will be picked at random. Are they less than 10% of all US adults? Yes, 100 is less than 10% of all US adults. Are the weights of US adults really skewed? It doesn't say here, but even 100 is pretty good for most everything. So if this question didn't say, you could justify saying, the question does not say that they're really skewed, but 100 is large enough for pretty much everything to be normal. So 100 is large enough. So we meet the conditions, which I think is the next page, or this page right here. Yeah, there we go. Says it anyways. So we do not want above 190 pounds. Well, that solves everything, which I don't want to do. I'll let the slide say it, and I'll talk through it. So to view it on the screen, which is always good, what we have going on right here is if we expect one adult to weigh 176 pounds, what would we expect the average of 100 adults to be? 176. Yeah, I mean, if one adult weighs that, and then we average together a whole bunch of adults, makes sense. Our new standard deviation, because the new distribution is going to be more normal and more what? More water. Tighter. I couldn't go any further. Elbows. So it'd be more normal and more tighter by a factor of the square root of n. And do you see that being done on the formulas here? So our new distribution meets the 3 conditions, random 10% and normal or large enough n, later condition, meets the condition of large enough n, and thus we can say we can use the normal curve now. Since we can use the normal curve, all we do is go to a site like the David M. Lane applet or this nice picture right here and just put 176 at the center and then go up 6.1 and down 6.1. And then we can figure out the z-score. Now this does seem unlikely because it's a z-score of 2.295. So above 2.295, and I think it's on the next slide, 2.295 is only about 1% of the area. You can enter this in context or use the z-score. How do we do the z-score? Just like we did before. We do not want to observe 190. That is an observation, which is a sample mean, which we could observe in a sample. Does that make sense? We have what we expect. We expect the mean, which is 176. All we're going to do is find their difference because a z-score is how many standard deviations the observation is from the mean. That's all a z-score is. How many standard deviations is the observation from the mean? And if you look, you can visualize it. You can say, oh, 1, 2.3 or so. It's 2.3 standard deviations above the mean. Is that kind of odd? Is it? Is 2 standard deviations pretty odd? It's kind of odd. And with that in mind, we would see that our balcony would work about 98.91% of the time with 100 random US adults on it. It's a little bit scary to think it's got a 1% chance of breaking, right? A little bit scary. Little bit scary. And 1.1% chance it'll break. Would you take the risk? That's where they make their decisions. So this is the biggest thing. This is where people get messed up. We've put this on the test before. One, I keep reiterating, you learned two things in this chapter. You learned about the sampling distribution, and you learned about sample statistics and all this stuff, but it gets confusing because we have categorical data and quantitative data. And one thing people think is that, oh, my population is right skewed. If I just keep sampling the population will start to look normal. So imagine test scores have a left skew. If I just take 500 students from their chemistry exam have left skewed, and I just take a sample of 500, will that be normal? The sample of 500 will look what? Chemistry exams have a left skew. I go out and sample 500 students, it'll look skewed. Nice job, Montana, extra right there. It'll look left skewed. Does that make sense? And that's what this is showing, that if you sample, your sample will just look more like the true population. But what if I go out and I take 25 students and I average together their exam to see kind of what a good idea of what the average might be of this exam? Then I'm drawing that from a population that is more normal, because now I'm looking at the average of 25. That is the N we are increasing. You take 25 students, you take all their exams, and you average them together, and then that's going to be tighter and more normal, that distribution, which you're not actually making that distribution. Does everyone get that? What you are doing is you're going to that left skew distribution, or let's say right skew, because this one's right skew. And what you're doing is you're sampling 25 students, and then one of your observations, which we'll be able to see where this lands. This landed, usually shows the blue dot here, doesn't it? It doesn't show it. Let's say this landed right here, and this, wherever this is inside of this theoretical distribution. This is like a theoretical that exists for all samples of sample size 25. Does that make sense? Because you're not actually getting this distribution. You're getting one sample. Once again, as I show it, you're getting one sample inside of this when you go out and sample. But won't it be more likely that your sample will be closer to the mean of 25 when you average them together? And let's put a little line. So in class, I think this one worked out really well, because look where that landed. That landed where? Right at the mean. Because it makes it more normal and tighter. You're sampling from a different distribution. You could sample just one person, and as we keep saying, if you sample one person, which I can't do with this, it'll just look right skew on this distribution, because it's just going to rebuild that. You'll just build that back up. But the distribution of means is more normal and tighter. So we got time. Who wants me to do 15.1 or 15.2? What question do you want me to do on it? I'll try to hit up at least 2 or 3 questions. If you're like, do this one, do 15.1 problem 2, 15.2 problem 3, I'll try to do those right now. We'll try to knock those out. Any question you want. You're stuck on, what is all this nonsense? Any questions? We got 12, 13 more minutes. I feel like today's lecture and last time's lecture really cover these very in depth. These are harder chapters people get destroyed on. Any votes for 15.1 or 15.2? 0.1? Okay. Any votes on a question? The Apple question? Wait, I'm doing the quiz. Homework. Let's do it. This will be in the video for forever to see. The Apple question. They online want that. They like it. Okay. Apple question is the last question. So we work for a crooked Apple company. Now read the question. It says that our truck will be rejected if 10% or more of our apples are bad. We want our truck to be accepted. Suppose 12% of our apples are bad, and that Walmart, I'm using them as problem, will be sampling 125 of our apples. Now we know by doing long research on our company that what percent of our apples are actually bad. You got it, say it again. 12%, because it says suppose 12% are bad. So what is the truth? So what's the truth? What percent of our apples on the truck are bad? 12%. So when they go out and sample, what should they see? What's the most likely thing for them to see, I should say? 12%. So guess where that goes? I'm putting this in as a placeholder. Might be close to their answer, but that is just a placeholder for the moment, just so we can see a distribution. But does it make sense that at the moment, 12 is the most likely thing for them to see? But now, let's go back, and this is from the previous chapter. So we're doing P times Q over N square root. Well, wait, what is P? Is P 10% or 12%? Which one's P? P stands for the what proportion? Careful, careful, careful. P stands for the true proportion, 12. P hat stands for what you might see in a sample. Now think, they're gonna sample and they don't wanna see 10%. Do you see how that's a P hat? P hat is in a sample. They're gonna sample and they don't wanna see 10%. But the truth is 12%, so it's the true proportion. So when we calculate the standard deviation for P times Q, does everyone see how I got Q? They add up to 1, over N, square root. That is our standard deviation. Copy, paste, and now here's our new distribution. Sometimes it does this. If you delete a number or two, it'll show it eventually. And that should be good enough. No. Do what? Say it again. Yes. N was 125. Yes, it is. N was 125. Exactly right. Great question. So here we are. Now, they are only going to accept our apples at 10% or bad. Please, somebody try to figure out the z-score for me by just kind of using, what is the z-score of 10%? You could figure it, observation minus mean over standard deviation. This is a great test question. What's the z-score? What's the observation? It's what? That's what the mean. That's the mean. So the observation is, I've got my cursor over it. It said they don't want to see what? So that's the observation. So 0.10 minus the mean. What's the mean of this? 12%. So that's negative 0.02 over, what's the standard deviation? Negative 2/3. Do you see it? Do you see it? The formula we just did is P hat minus P over standard deviation of P hat. So P, questions? That's the z-score. Do you see, does this look where 10 would be at? Let me put in the exact numbers here. I wanted to put that in so it looked a little better. But if I put below 10, does that look to be negative 2/3 right there? As in this is 0, this is negative 1, and that's negative 2/3. Does that make sense? Because 11, 10, 9, does that make sense? Because there's 3 numbers. So just visually, you want to double check. If you get a z-score, draw it out. Because if you got a z-score of like negative 8, it doesn't look like that, does it? Draw it out visually and take a look. Now you want to know the cool thing? This is near a number. Negative 2/3. I'm saying point. I'm going to take a guess. Take a guess. Oh, no. Oh, wait, am I in a meeting? I hope I am still. 3 decimal places. There you go. That's when you've done this class too much. Not too much. You just, I don't know. The reason being is I know the z-scores. No, I said the z-score is negative 2/3. I know a trick. Do you see how these are z-scores now? What's that right there? Do you see where this is negative 2/3 right there? And then if you were to go below this, if 50% is in the middle, what's down here? If 50% is in the middle, the bottom portion right now is what? So do you see how this graphic right here, when we view this, I don't know why it's not showing it now, is at 25%. And I went a little bit less than it. Does that make sense? You're not supposed to be able to figure that stuff out like that. It's just because when I see negative 2/3, I know that is basically the z-score for the Q1. I knew that was the z-score for Q1, so I was able to compute that in my head. So that's why the empirical rule and stuff like that really helps. and I just got lucky on the decimals. I went a little bit lower than it. But, you know, we could do you guys want to do one more? We got enough time for it. We could talk through one more. You guys want to do the bank problem here? All right. The bank problem actually covers, I think it's this one. Yep. Like I said, I've done this class a lot. So here we are. Don't have me do calculus. I don't remember how to do calculus. If you want to put Brian's foot in his mouth, just be like, Brian, do this integral. Solve this integral for me. None on the street. No one gets that joke because it's an inside joke. Okay. Based on past experience, the bank believes that wow, this is awesome. They know that 12% of their people, why am I liking this? Why am I liking 12%? Whoops. Yeah. I don't got to punch a new thing in. The bank expects 12%. They're going to loan out 400. So what do they expect to see when they do these loans? They expect what percent of people not to pay? They expect 12%. The mean of this distribution, that's what it stands for. The mean of the sampling distribution with the sample proportion is equal to 12%. The standard deviation is equal to P times Q over what? And finally, square root. Delete decimals. Done. Change it. Good. Okay. Check conditions. Condition 1. We forgot them. Random. Condition, so they're going to talk to random people. On the test, it should say random. I want to make that clear. On the test, it needs to say random. We've tricked people before. I know this problem doesn't say it. We will assume, but on the test, it needs to say random. Condition 2. We're a large national bank. Do you think this is less than 10% of all customers? Yes, we probably have more than 4,000 customers. Condition 3, pause. Pause, pause, pause. People will either default on the loan or they will not default. Success, failure. That's the key. Because that's also going to dictate what formulas we use with P times. If you see P times Q over N square root, it's success, failure. If you do standard deviation over the square root of N, then that is the large enough N condition. Because it's over the square root of N. Does that make sense? So if it's P times Q over N square root, it's success, failure. If it's standard deviation over square root of N, it's large enough. If we have 12% we expect to default out of 400, how many is that? 12% out of 400 is, NP would be, what's 12 times 400? 48. And that means the complement of that is 352. So you do 400 times 12%. Does that make sense? And then you could do 0.88 times 400 and you get 352. So it all make logical sense. And so we meet all the condition with reasonable assumptions. Last killer question. We've already drawn out our work though. So meeting the conditions means it's normal, means we can use the empirical rule and all that stuff. We're gonna close our doors if 14% don't pay. Do you see where 14% is at? It's right about here. The z-score for 14% is a little bit higher than what? Yep, it's about 3.2 or 1.23, I think. So we take this minus this. You see observation minus mean over standard deviation. I said 1.23. Brain's working right today. So 1.231 is the z-score, but we don't need to enter that in. We merely go to above, and we go to 14%. Make sure it looks right graphically, because we say it's at about 1.23. Above 1.28 is 10%. We're a little bit higher than that. 0.118, I think, is the answer. If I get the second one, I'm just going to say, like, wow. No! Gotta give one last shot here. We got time. I'm going for the final shot here, everybody. Woo! All right, what was it? Okay, it rounds to that. About 11%. I don't know. I have fun with those. That's my test of can I get these things right by. But the reason I show you guys that, and I want to say this is my last 2 minutes. The reason I do that is because people keep saying to me, Brian, we don't have the applet on the test, which I hear that all the time, and I hear that throughout the whole course. Like, Brian, we won't have the applet. But I say to people, if you know the empirical rule, you can usually get very close. And I can get close enough that I can get the answers right. And I teach this course. I know. But if you know the empirical rule, you could have told me that this percentage is between 2.5 and 16%, and it's going to be closer to what? Do you get why 2.5 and 16? 2.5, 16, does that make sense? And it's going to be closer to which one of those? 16. If you had guessed, you might have told me something like, it's probably about 11, 12, 13%. I don't know. You probably would have said something like that, right? I know a few other tricks that you don't know, but I think many of you would have guessed around 11 to 13% or so, and you would have been very right. Does that make sense? That's why we learn the empirical rule. That is knowledge you carry with you at all times when you have to talk about probabilities according to statistics. You guys are good to go. Great class, great lecture, and head on out. 1 minute early. It's the way we roll. I have a lot of fun with these homeworks. I've literally probably done these homeworks 200-300 times. It's like, oh, let's do this one. I don't know. Caffeine's wearing off now. You weren't in my office when I was on a caffeine kick. That was stat lab today. I drank like 2 cups of coffee and it's all crazy. Does anyone do Starbucks stars? No? You guys got to do them. Do you guys drink coffee at Starbucks? Get the app. Get the stars. Free drinks. See you guys. You're welcome, guys.
Go see something beautiful.
What's that say right there? 9. And then I've been collecting them only since like the start of the year. And those are any drinks.
Do you not use them?
The problem is, so the one on campus will give you stars, but you can't redeem them. Also, I think any drink at Starbucks, like the $5-6 drinks, are way too overpriced. They usually get $1.30 coffee, and then that's New York accent. And then you can get like double stars, and there's things you can do. Like, there's all these things you can do to get extra stars. And but then when my girlfriend and I go get a drink, like on the weekend, you can get grande or venti, triple shot, mocha frappuccino, like a $6-7 drink. So I've got like $50 worth of drinks right here. And I've probably spent like $200, but $50 worth of free drinks for $200 is probably, it's very good. At least you get something, right? So it's got it. Get the Starbucks stars, get the app. Hopefully Starbucks, maybe they'll give me some stars for promoting them. Questions?
Tomorrow, office hours.
I do. I can figure out when they are. I think we're recording here. I'm going to stop recording.